Welcome everyone to this explainer. You're tuning into the Foundry by Forge College. So in our last lesson, we actually explored the key figures and the influential writings that sparked the whole cypherpunk movement. We talked about their bold ideas, their debates on anonymity, and, their big visions for a totally free digital society. But today we're transitioning from the rhetoric to the reality. We're going to put down the manifestos and pick up the actual clunky 90s tools they built. I'm talking about the kind of tools that required a screeching dial-up modem, a whole lot of prayer, and just an incredible amount of patience to make those lofty ideas a concrete reality.
Okay, let's just dive right into the schematic overview for today. We're looking at the privacy stack, Layer 1 confidentiality, Layer 2 metadata obfuscation, and Layer 3 verifiable evidence. Then we'll run through the 1993 manifesto experiment, and finally, wrap up with the limits and lasting legacy of all this.
All right, Section 1, the privacy stack. Let's start building the blueprint.
To kick things off, we need to introduce a really foundational concept, and that is the privacy stack. You can consider this your engineering blueprint for digital anonymity. Now, early on, these pioneers realized something absolutely crucial. Privacy isn't just a single magic switch, right? You don't just hit a button on your beige plastic keyboard and instantly become a ghost in the machine. Instead, privacy is actually made up of orthogonal or completely distinct layers. Each layer addresses a very specific, separate type of data leakage. Think about it like a fortress. If you only build up one wall, your whole defense can still easily collapse from another angle. So let's walk through the 3 steps of this schematic stack. Starting at the absolute bottom, our foundation, we have confidentiality. This is all about protecting the actual content of your message. Moving up to the middle, we have metadata protection. This is about hiding the connections, like who is talking to whom and when. And capping the whole thing off at the top, we have verification, which is providing mathematical evidence that something happened without ever giving away your identity.
Let's look closer at Layer 1, confidentiality. To tackle this absolute foundation, keeping the actual content of your message a secret on an entirely open network where literally anyone can snoop, the cypherpunks leaned heavily on a brilliant mathematical concept. It's called public key encryption. Let's use a relatable metaphor here. Imagine an absolutely opaque envelope, but instead of just licking it shut, you lock it with a perfectly fitted padlock. You encrypt your message to your recipient's public key, effectively snapping that padlock shut. Now, only the intended recipient, who possesses the exact unique private key, can unlock and open that envelope. This ingeniously solved a massive age-old headache: how to secretly share a password before sending a secure message.
But of course, there was a catch, and it created quite a dilemma. Symmetric encryption is super fast for encrypting lots of data, but it requires that risky pre-shared key. Asymmetric, or public key encryption, is highly secure for sharing secrets without meeting up first, but computationally, it's painfully slow. So the crucial point here is how tools like PGP, Pretty Good Privacy, brilliantly combine these two methods. They use the fast, symmetric cipher to encrypt the bulky payload of the message itself, and then use the secure asymmetric public key method to safely wrap and send that symmetric key to the recipient. It was hybrid encryption, elegantly giving you the absolute best of both worlds.
Moving on to Layer 2, metadata obfuscation.
Because protecting the content simply isn't enough, we gotta move up the stack to Layer 2. Even if your envelope is perfectly opaque and locked tight, an adversary can still see exactly who you're handing it to. They might not know what you're whispering, but they know you're whispering to a specific person every Tuesday at 2 a.m. That is metadata, and it is incredibly revealing. To fix this, cypherpunks utilize the mix network. I want you to picture a relay orchestra. Instead of one musician handing a piece of sheet music directly to another all the way across the room, the sheet music is passed around the entire orchestra. It gets decrypted a little, reordered, and forwarded in batches. It passes through several players who each alter it just slightly. By the time it reaches the end, no single musician knows the entire tune from origin to destination. David Chaum's mixes in the 90s remailer services did exactly this, to completely break the linkability between sender and receiver.
But, as you might guess, there were severe trade-offs. Just imagine trying to do this on 90s dial-up speeds. You'd literally be waiting until the new millennium for an email to actually send. Adding a mixed network meant adding severe network latency. It was not snappy. Furthermore, it required cooperative infrastructure, meaning you were relying heavily on trusting random, volunteer relays across the globe to play fair. And to stop adversaries from just analyzing the timing of when messages went in and came out, it introduced the need for cover traffic, basically sending fake noisy messages just to confuse onlookers. So metadata defenses weren't just a simple software toggle you could switch on. They were incredibly slow, clunky, and honestly, socially complex to maintain.
All right, Layer 3,
Verifiable evidence.
To prove something happened without exposing your identity at the top layer, the core primitive is the cryptographic hash. Think of this like an unforgeable digital fingerprint. It's a short, fixed-size string of characters generated from an entire digital file. And it is strictly a one-way street. You absolutely cannot reverse engineer the file from the hash. This brilliantly illustrates our notary stamp metaphor. If you take that hash and publish it alongside a public timestamp, it acts just like a notary stamping the corner of your sealed envelope. It mathematically proves that a specific document existed at a specific time without ever revealing a single word of what's actually inside the envelope.
Now, let's tie this all together with the 1993 Manifesto experiment.
Let's put our entire patent-style blueprint into motion. Imagine you're sitting at your bulky desktop in 1993, listening to the screech of your dial-up modem, and you've just written a revolutionary, highly sensitive manifesto. Let's walk through the first half of the workflow. Step 1. You hash your manifesto document, creating that unforgeable digital fingerprint. Step 2. You encrypt the actual file using PGP, creating opaque envelopes wrapped specifically for your trusted friends. And Step 3. You take that fingerprint, the hash, and you publish it on a very public bulletin board. Boom! You have now officially stamped it for the public record without leaking a single word of your actual text. But we have to finish the workflow to stay totally safe. Step 4. You need to hide the metadata. So you send the encrypted PGP files through our Relay Orchestra, a chain of mix remailers, so nobody monitoring the web can trace those emails back to your IP address. Finally, Step 5. Let's say years later someone challenges your authorship or the timeline. Well, you can simply reveal the original document. Anyone in the world can hash it and perfectly, impartially verify it against that public bulletin board post from 1993. The math allows them to know with absolute certainty that you possess that exact document back then. It's just an incredibly elegant workflow.
So what happened? Let's talk about limits and lasting legacy.
With all this brilliant cryptography at their fingertips, why didn't these tools immediately take over the world? Exploring these operational failures is actually a big part of our learning programs at Forge College, because frankly, you really have to understand the past to understand the Web3 architecture of today. To summarize, while the cryptographic mechanisms themselves were absolutely genius, combining them created massive operational friction for everyday users. PGP was amazing, for sure, but it suffered from severe key management complexity. Users had to manually verify and sign each other's keys in a web of trust. Mixed networks had terrible latency and relied on trusting random server operators. Blind signatures, which were used for early eCash experiments, still relied on a centralized issuer, which created a massive single point of failure. And hash timestamping? That depended entirely on the archival persistence of random public forums. If the forum went down, your proof was just gone forever.
The absolutely crucial point I want you to take away from this era is that the failure to achieve mainstream adoption was not because of broken math. The math was incredibly sound. It failed because of clunky user experiences and the heavy reliance on social trust. Severe usability friction, complex manual key distribution, massive dependency on volunteer infrastructure, and a complete lack of broader network effects basically meant these tools mostly remained the toys of brilliant hobbyists and highly technical cryptographers.
Which leaves us with this provocative thought. How could these clunky, isolated 90s privacy tools be optimized, automated, and combined to finally create decentralized digital money? Well, that is exactly the puzzle we're going to be piecing together in our next explainer on digital currency. To continue exploring this fascinating history and to dive deeper into all things Web3, make sure to visit us at forge.college. Thank you so much for learning with me today, and I'll catch you in the next one.